Follow-up questions, there's been plenty of time after Simon's presentation to ask them, and then we'll go into closed session.
All right, thank you, and thank you all for being here. I'm very excited to present some of the work that I've been doing over the past 5 years in preparation for my PhD. And the title of my dissertation is Inverse Design and Analysis of Crystallization Pathways of Colloidal Systems. And so there's going to be two main parts. I'm going to talk about inverse design, and I'm going to talk about the analysis of pathways. And then I'm going to conclude by discussing some of the software that I've been working on. So I want to start by introducing the general problem space. We're looking at nanocrystal self-assembly, and this is a figure. This is a figure I took from a review by Bolz and coworkers, who really nicely outlined all the kinds of ingredients that go into crystal self-assembly on a nanoscale. And at the core, we usually have some kind of building block. So those are the elements that really make up our material. And in this space, we can be really creative. We can have shapes and particles, all kinds of different shapes. And the second ingredient is maybe the surface of these particles. So we can modulate effective interactions by coating these particles with maybe ligands or DNA and making them sticky or squishy. And then the final ingredient is the environment. Are we in some kind of liquid, or what's the concentration of salt in this liquid, the pH value, etc. All of this is going to determine what we will get by mixing these things together, and we can then measure what we find. Maybe we just get some kind of soup, or maybe we get actually some kind of crystalline structure with specific properties. So designing these building blocks is an example of a forward problem. So you can go into the lab and come up with some kind of new particle. Maybe you found it on accident, or maybe you specifically designed something, and then you throw everything together, either experimentally or maybe in simulation, and you can measure your outcome. So maybe you get the structure or not. Maybe you have something that has specific photonic properties or specific ductility at various temperatures. So this process of designing a building block and then just looking what we get, essentially, is a forward problem. And if we have atoms, this problem space is somewhat constrained. There's only so many atoms available. There's only so many atoms that we can reasonably use. Like, we don't want to use radioactive materials, for example, in certain segments. And there's only so many ways that we can combine these atoms without breaking the fundamental rules of chemistry. But with these nano building blocks, we can be much more creative, and this problem space is highly combinatoric. So we have like infinite choices, essentially. So this is very difficult if you wanted to exhaustively search the space. So instead, what might be a more targeted approach is addressing this inverse problem, where we start with a certain structure that we're targeting, maybe a structure with certain properties, and then we try to determine what building blocks do we need to assemble such a structure. So this approach is way more targeted, and it's especially susceptible to computational approaches, because we can very fast propose models and test them, or we can use theory to devise methods where we directly optimize certain particles for certain properties. So this is going to be what I'm going to present first, a method to design models, optimize models for specific target structures. And so before I do that, I want to very briefly introduce the kind of model that I'm going to talk about, and that is an isotopic pair potential. A pair potential is a field, essentially, around a point particle. And it's a simple model, but it's still powerful, as I'll be able to show you. It's radial isotropic, so we can imagine that we have some kind of point particle, like a marble like this, and if we have another marble we can define an energy that is describing the interaction between these two particles. And the very basic interaction is what we usually refer to as a Hart sphere or repulsive interaction at short length scales. So we can imagine that we have these two models, and wherever they are in space, it doesn't really matter, the energy is just zero. But as they get closer together, so as we get here, this is the distance between these two particles, and this is the energy. As we get closer together, all of a sudden, the energy spikes into infinity. And so in reality, the equivalent would be that I can't really push these anymore together. So we can describe this kind of interaction with a mathematical function. Very simple, we just say 1 over r, that will spike or happen, that will diverge to infinity as we get closer together. On the flip side, we can flip this around and describe an attractive interaction like this. We say the energy becomes more and more negative as we get closer. And so this is a slope that our two particles will fall into, essentially. And what we created basically is a black hole. So these things are just falling into each other, and we would need infinite force to actually get them detached again. However, the trick is now that we can essentially combine these two things, the repulsive energy and the attractive energy, and we are defining a potential that looks like this, which still diverges as we come closer together. It's still impossible to have these two point particles overlap, essentially, but they still attract each other at finite length scale. So the combined effect is that we have some global minimum energy here at a what's called equilibrium distance, and I tried to shade this, like illustrate this here with this shaded field. So the red here means high energy. None of these two particles want to be that close together, but they still want to be somewhat close together. So they come close here, it gets greener and greener, and then eventually they're coming too close together. And so this model in this kind of form was originally proposed actually in 1924 by Leonard Jones, and it's been surprisingly successful in describing a lot of real world phenomena. So this is a very accurate model for the interaction of noble gases, for example. And you can tune this potential by changing these parameters here, sigma, which is some arbitrary length scale, and epsilon, which is some arbitrary energy scale. And you could also change the slope of these repulsive and attractive ends here. However, then it wouldn't technically be not a Leonard-Jones potential anymore. And it actually makes a lot of difference of how steep this potential here is. That's something that my coworker Alan showed in his work. So this model has been very successful in describing fluids and gases and liquids. And it turns out that you can actually also use isotopic pair potentials for the modeling of self-assembly of structures. So this is an example of the oscillating pair potential, which was shown to assemble a icosahedral quasicrystal under certain conditions. And it's actually a little surprising at first to think about potentials like those creating structures like that, because these structures are somewhat breaking symmetry, whereas this is really symmetric. It's radially isotropic, so the same in all directions. But in fact, we can play around with this potential, changing the depth and relative depth of these belts, for example, and find that they will assemble all kinds of different structures, simple to complex. And that is something that was showed by Michael Engel and coworkers. And this is a perfect example of a forward design approach. So they took this model and basically exhaustively searched all kinds of different variations of this and observed what would be happening. And you can try to draw conclusions from that. However, this work kind of inspired me to think about using this kind of model for inverse design, trying to target a specific structure and determining what model, what potential would we need to assemble such a structure. And so optimizing potentials for certain target states is actually a very old problem. It's not new. And this is I'm going to very briefly introduce a method that's been very popular in trying to optimize these kinds of potentials for so-called coarse-grained models, where we are bundling multiple atoms essentially into one interaction site. It becomes a marble, and we try to model the effective interaction between these molecules using this model. And so the iterative Boltzmann inversion is very simple in that it tries to find a potential that will yield a system that has this distribution of density. So here on the x-axis, we have the distance between points, and on the y-axis, we have a normalized density distribution. And so the way that we interpret this is that at this distance 1, the density is highest. So there's a preferred distance between particles within the system. And then there's a little bit of a dip, and so on and so forth. So there's a certain wave of particles, if you will. And it turns out that we can actually calculate what's called the potential of mean force. It's the inverse log of this distribution that is the free energy surface as a function of distance of this particular system. And the free energy, for all intents and purposes in this context, is a proxy for the probability of that specific property. And so this potential of mean force is the Boltzmann inversion. So we have the Boltzmann constant here to bring in some energy, and we inverted this distribution and took the log. And this potential of mean force is actually the exact potential we would need at infinite dilution for this kind of distribution. So this is a little bit of a paradox, if you will. The potential would be exact if we were infinitely far apart, so like no particle is actually interacting, but it's presenting a limit that we can exploit. So the potential of mean force in this approach is used as an ansatz function as a first guess at what the potential might look like. And so we will simulate it. We then measure the G of R, the distribution of density here, and we can compare this density that we get with the density we want, and use that to update this potential. So we take the one that we have right now, and we subtract this term here, and we get a new potential at the next step. And then you can probably already guess this. We use this again. We simulate a new system with this potential. We get a new function, new density, and as this Gi here, the density at our iteration, becomes more and more similar to the G star, the one that we want. This fraction here becomes 1, the log of 1 is 0. And so this is how we converge this potential. The iterative Boltzmann inversion cannot directly be used to optimize potentials for structures, and that is because the density distribution in structures is much more discrete. However, it was shown by Lindquist and coworkers that you can use a very similar technique, which is directly derived from the relative entropy framework, which I won't be able to introduce here. But the gist is that this is a slightly more physically motivated and more general approach in trying to optimize potentials in a very similar way, like the iterative Boltzmann inversion. And using some constraints and some tricks, it's possible to use this technique here to optimize potentials that will self-assemble certain structures in 2 dimensions. So this would be a way to optimize potentials for structures. What I didn't quite like about this technique was that we needed these arbitrary constraints on the potential, and it also wasn't as numerically stable. These potentials would become somewhat complicated for the structures that I was interested in. And so I looked further in the literature and found a work by Edlund and coworkers who showed that you can design a pure potential, which is shown here in red or in gray, for a specific structure like this one, directly in Fourier space or inverse space for these structures. So the idea here is that because structures are periodic, we can express the energy much better in terms of steps or periodicity instead of distances. And what we can do is you can design a potential that has a low energy or zero energy at exactly these lattice distances here. And this would be the gray curve here. We can see that these dips at different specific periodicities. And if we invert this potential into real space, this is the gray line we get here, we still have a very complicated potential. But the trick here is that we can apply some smoothing function directly in Fourier space to simplify this function here, and we get something very smooth in real space as well. So this sparked the realization that we can actually use this kind of approach, this filtering approach or smoothing, to get simpler potentials that might be easier to map to a real physical model. So what we would call in real space smooth and few features would in essence be expressed in Fourier space as a suppression of the high k values in the potential. And so we can define a norm like this, which describes the complexity of the potential as a function of its Fourier representation times the k value, and then we square it to make it positive. And so the smaller this number is, the smoother the potential will be in real space. So to summarize, there are various different techniques to optimize potentials. I'm not listing all of them. There's way more. There's the Boltzmann inversion that I very briefly introduced at the beginning, which we can use very well for designing of potentials, optimized potentials for fluids and so liquids and gases, not so much for structures. There's the general relative entropy minimization idea that was shown by Lindquist and coworkers we can exploit for this kind of problem. And then we have this idea of designing identity cycling Fourier space to control for their complexity, if you will. And so I combined these two approaches. I said, well, I like this idea of optimizing potentials within this framework. I like the idea of designing IPPs directly in Fourier space and controlling the complexity in this way. And so we developed the Fourier filter relative entropy minimization. So it's relative entropy minimization with a Fourier filter. And so I'm going to very briefly introduce the concept. We have, like in the Boltzmann inversion, we start with some kind of function here, v of I, and then we invert it into real space to get something that we can evaluate the forces of. We'll assemble some kind of structure or not, and then we measure the density distribution in K space and apply an update to our potential to better match or to drive it towards the desired density distribution. So the in math is what it looks like. We have some kind of starting potential if we're trying. We measure the density distribution, we subtract the target density distribution, and then add that to our potentials updated. And the trick here is this term. Alpha here is just some kind of constant to reduce the step size for numerical stability. And then e to the minus dk is this Fourier filter. So k here again is the periodicity, and then c is our filter constant. And so if c is 0, then this term is 1, so there's no filter. If c is non-zero, finite, then we'll suppress all the larger k values within our update. And so this is the effect. If we try to optimize a potential for the CI2 structure, or BCC, without any filter using this kind of technique, this is one of the best solutions we found in yellow here. So you can see we can find a solution, but it looks somewhat janky, and all of these little features here and wiggles seem unimportant because we do know that there are potentials that will assemble BCC that are much simpler. And so if we increase the filter constant above 0, now we see that we can optimize a potential that looks like these blue lines here. And it turns out that we can actually control the complexity very distinctively by changing this constant. So for 0.1 sigma here, we get this slightly lighter blue curve. And you will notice that this curve has 2 minima here and here, whereas the one with the larger filter has this second well here almost completely suppressed. So we tried this for various structures, including simple ones like simple cubic and FCC, and we were able to show that using this kind of filter approach compared to no filtering, we are able to suppress all of these extra features that are unessential for the assembly of these structures. And on top of that, sometimes you weren't able to find any potential using no filter. So it's not just cosmetics in a sense, it's something that actually prevents us from using this technique to find potentials for slightly more complex structures. So in summary, the Fourier filter relative entropy minimization is physically motivated minimization of relative entropy, which I didn't talk about, but which in essence means you want to match two states as closely as possible. And the range of these potentials is actually independent of the range of this density distribution that we're trying to match. So both for the iterative Boltzmann inversion as well as for the relative entropy minimization, the way that it was published, the range or length of the potential is identical to the information that we put into the update. And then finally, we were able to show that applying this filter function, we could control the complexity and prevent overfitting of these potentials for the desired target states. So I'm going to pivot a little bit now. So we were able to find these models in terms of isotopic pair potentials that will assemble some desired crystal structure. What we were also interested in next was to find out how exactly are we getting from here to here. So just as a reminder, these energies of fields represent point particles in space that are interacting via this energy. They have forces that interact on each other, and they must in some way come together spontaneously to form something that looks like this, that is highly periodic and highly structured. And so this is the big black box that we want to get some insight here. And there's been a lot of work being done on the study of crystallization. And maybe one of the biggest mysteries is why does it happen? Why does it happen so fast? So there's a lot of understanding of how these, we can actually image these things and see what's going on. But what is still one of the bigger gaps between the literature and the theory and experiment is the rates at which these things happen. So before I can talk about the method and the results that we have, I need to introduce a few concepts. So first, I'm going to introduce the concept of an order parameter. So the order parameter is essentially a number that describes the macro state of the system. So you could imagine something from 0 to 1, for example. 0 would mean completely disordered, everything's random, everything's fluid. And then 1, it's like a perfect crystal. Everything's nicely structured and ideal, essentially. And the order parameter that we usually use when it comes to crystallization is crystallinity. So I found this nice quote from a paper by Alan and coworkers who said the order parameter employed for a crystal nucleation process should be the number of particles that are crystalline. So this is what we usually refer to as crystallinity, and we can either take the number or we can take the volume of the crystal. But sometimes it's maybe a little better to not use every particle that is in the crystal or that is crystalline, but to actually look at the largest cluster. So we have something that forms the crystal, and we will only count those that are in the largest cluster. So how is it usually described? So we have various modes of crystallization. So we have homogeneous nucleation, where we have some random fluid, and all of a sudden, completely spontaneously, a bunch of particles start to cluster together, and they form some periodic structure, maybe they increase their density locally, and then it grows from there. We have heterogeneous nucleation, where we may have some other element in our system, such as a wall, and this wall here may be a pattern of particles that then actually will help trigger this process of some particles will attach and then grow from there. And then we have spinel decomposition, where things are essentially just falling into place spontaneously. There's no energy barrier for that. However, if you look at nucleation, the kind of processes that I'm going to study here, the big question is always, why does this even happen? Because if two particles, we can imagine that if particles are in fluid, they're somewhat happy about that. They can arrange them any way they want. However, once they come together and form a crystal, they're even happier. So this is what we describe in terms of energy. So we designed our energetic model such that the energy is lower in the crystal. So for each particle, that means it's much happier. But while the particles here inside of this nucleus are very happy, the ones at the surface are not, because they are kind of forced into this structure, but they still need to deal with all of these particles outside of this nucleus and in the fluid, and they don't have the freedom to move around in any way they want to kind of accommodate whatever they're facing there. And so this is what we describe as the surface of this nucleus, and then everything else is the bulk. And that is kind of the crux of the problem. So as we form this nucleus here, let's say we start with 1 or 2 particles, the energy at the surface is actually larger, and so the overall energy increases, and the energy in the bulk is smaller, but the two together are larger. As the nucleus grows, at some point we reach this top here, where the nucleus is so large that the surface doesn't really matter anymore. There are way more particles inside this nucleus than at the surface. It's just geometry. And eventually, this thing is so large that we don't really care about the surface anymore, and it just grows into the bulk and takes over the whole system. And so this is and we can use heterogeneous nucleation to kind of make this a little easier. The surface is already here, but there's still a surface around it, so it makes it easier, but not completely free. And this is kind of the big problem. We need to overcome this large free energy barrier here to even start this nucleation process, and it still happens. And so one idea to explain this a little bit, why it happens a little more often than we think in this classical model, is more complicated nucleation processes, such as two-step nucleation. So the idea is that we have a solution of particles that are somewhat happy in their solution, but they would be much more happy in the crystal. Maybe there's some kind of intermediate state here that is somewhat similar to the liquid and somewhat similar to the crystal structure that will eventually form, but it's easier, it's somewhat in the middle, and it's easier to form. So while this isn't ideal, it's maybe a little easier to get there, and then eventually we can fall into the final crystal structure. So this would be a two-step process. We first form some other structure, and then we form the final structure. The other question is, what are the prevailing the main modes of this process? So we can have density, and the size, for example, and we could say, well, maybe these particles come together first. They first densify spontaneously, and then they say, well, we're already close together, so why not order as well? Or the other way around, they spontaneously order, and that order allows them to then come closer together. Or maybe both things at the same time. So I'm now going to introduce the technique that we're going to use to study this process. So there's been somewhat a little bit of a revolution in the field in trying to embrace machine learning techniques to identify these processes and analyze these processes. And this is one way we can do this. So let's assume that we have some kind of particle with a local environment here, surrounded by these 8 other particles here, and they form some specific arrangement. And we can then further assume that we can describe this arrangement in some way. So one very simple way would be to count the number of particles that are at a certain distance. Or we measure the angle between this one, and this one, and we measure all the angles. Or we use more complicated techniques. But no matter what we do, we have something that describes this environment. And with machine learning, the idea is really that we're a little more agnostic as to what we feed into our algorithms and what we get out. So we say, let's propose a bunch of what's called descriptors, something that describes these environments, and then we just attach them to each other. And what we get is a long string of numbers. And these numbers here, we get one set of numbers for every particle in the system across all times. And this is what we will refer to as the descriptors, the descriptor space. The one challenge here with the space is that D is very large. It can be small, like I said, we can only look at very simple descriptors, or it can be hundreds of thousands of numbers. And what we do to kind of get a hold on this massive amount of numbers is we apply a technique called principal component analysis, which is absolutely standard to try to determine what are the most important directions or features in this space. So I'm very briefly going to introduce this. So if we have let's say we have a point cloud like this in 2 dimensions on some arbitrary axes. If somebody asks you to describe this point cloud, you might come up with, well, it seems like there's 2 directions here. One, it's a little tilted, and it's a little wider in this direction and a little thinner in this direction. And PCA does essentially exactly that. It's trying to determine what are the principal directions here that explain most of the data's variance. So the idea here being that we can find these directions and measure the variance. And then we can reduce the dimensionality of this space by dropping off all the directions that don't seem that important. So if you wanted to reduce, for example, from 2 dimensions to 1 dimension, in this case, we would tilt this point cloud, and then maybe we drop this direction completely, because it's not that important in describing the data. We still learn a lot by just looking at that one direction here. So in essence, it identifies orthogonal directions that explain the data. So we can use that, and so now we've reduced our space from n entries here and arbitrary d dimensions to 20 dimensions. So we've really, by many factors, reduced the data size. And now it becomes tractable to apply more complicated advanced techniques to identify even lower dimensional spaces. So we use a technique, the UMAP algorithm, to further reduce the dimensionality of this set of numbers to 2 and 10. And we will only do this on a subset because this algorithm is much slower than the PCA algorithm, and so we try to reduce the computational domain here by only applying this to a subset of the data. And what we get is a 2-dimensional representation of this space. And so in this case, this is an illustration. We see that we have 4 point clouds, and this cloud essentially describes groups of particles that have similar environments. And the idea is now to automatically identify these groups. So we want to color these clusters. And for this very simple set here, we could do that very easily by hand. But we can also use algorithms that do this automatically. And we will actually cluster the 10-dimensional space and not the 2-dimensional space to preserve a little more data. But it's not very easy to visualize the 10-dimensional, almost impossible to visualize the 10-dimensional space. And then the final step is to take this representation, the PCA reduced space, and train a model on these colors that we get. We can do this step very quickly, and then we can train a model that is fast in predicting for each and every line here what the color is probably going to be. So we get one color for each particle at every step, saying, okay, it probably belongs to a certain group of particles that are similar. So the benchmark system that I applied this to is the Weeks-Chandler-Anderson potential. It's potential that is used to approximate hard spheres, so the marbles that I showed in the beginning, and it's in essence the repulsive part of the Lennard-Jones potential. So we only look at repulsive. As long as these point particles are far away from each other, they don't interact at all. Once they get too close, they don't want to overlap. And we do this at a positive pressure to kind of compress these point particles or spheres together. And it's important to know here that there are certain preferred ways that spheres want to pack together as you compress them. One is hexagonal closed packs, and we have these three layers here with two similar or identical layers, A, B, A. If we took actual hard spheres, like actual marbles, and were to compress them, this would be the best way to closely pack them together. And then almost equivalent, but a little different, is the face-center cubic packing, where we have one of these layers here, the top layer, rotated. So you probably will see this, that this top layer is just turned by 180 degrees in essence, essentially. And so we're probably expecting that our spheres are going to pack somewhere like this. So this is the point cloud that I showed the illustration earlier, but now for real data. So this is all the environments mapped into 2 dimensions using PCA. And we can see, and this is colored by the time. So it goes from dark to bright. And we can see that there's somewhat a cloud at the beginning, and then there are two main groups here at the ends here, and maybe 2 more here. And we then map this space using this Newman algorithm, which is now giving us a slightly different representation, which has more meaning in terms of distances between these points. So we can see that now we still have this cluster here at the beginning, and then we have these 2 main clusters, which are more distributed in terms of their time. And now we'll apply our clustering algorithm to identify the environments that are more similar to each other than others. And so this is the result. We see that there are 4 main clusters, or 2 main groups, and 4 clusters in total. And it might be a little surprising to see that there are 2 groups here for this group. This might be this can be explained by realizing that the clustering algorithm is applied to 10 dimensions and not 2 dimensions. So this extra difference between these points might not be visible in the 2-dimensional representation. And so this is a movie of the process of nucleating and growing a crystal using these WCA spheres. It's going to be really fast, so I might play it multiple times. But what we see here at the beginning is that we have a lot of these green environments, or environment 1, and we identify that to be associated with the disordered fluid. There's no order in the system. And to make this better visible, I made these points smaller, so it's very easy. It's easier to see the actual crystal. And we can then start the movie, and we see there's a lot of orange at the beginning, and a lot of blue, and then the orange and purple is kind of taking over at the very end. So we can compare this identification of our crystal with established techniques like polyhedral template matching, and we can see that these blue environments here are corresponding to what is identified as HCP by polyhedral template matching, and these purple and orange ones are identified as an FCC structure. And so if we look at the concentration of these different environments over time, we see there's, as expected, there's a lot of green particles at the beginning. And then there's, interestingly enough, this local maximum of random hexagonal close packing in the system. So the blue particles you will come together and will then transform into orange and purple. And so there's this maximum here where the system is now essentially completely ordered, and eventually transforms into a SEC structure that's stretching the bulk. Now we wanted to also look at slightly more complicated systems. This is A15, which is a complex metallic compound. And the A15 structure is interesting because it has two Bicop positions. So two particles in the 2 points in the unit cell that have different symmetries. And we were interested in if we can pick this up. So this is what we found. We can show that there is some fluid environment at the beginning. Then we have this purple environment taking over after dropping the temperature here at this step. And then eventually the system will have a higher concentration of these blue environments. And you can see very nicely that this purple environment is essentially translating and forming into a crystal structure. And we compared those again to polyhedral template matching, and you see that these purple environments here correspond to an icosahedral arrangement of particles, and the blue particles to something else. And this something else is the second microposition. So we can visualize the unit cell here like this, and we see that these things very nicely correspond. So to conclude this study of crystallization pathways, I wasn't able to show you all examples, but what we saw is that we can use this unsupervised machine learning approach to identify or discriminate very well between fluid and structure, and we can try to identify environments that are somewhat crucial for this crystallization process. We also saw that the environments that show high order in the crystal are usually already present very early on in the process. So they're everywhere in the fluid, and they're present right from the start. And then finally, we saw that the crystallization processes are two-step processes. There's usually some kind of intermediate environment that is more similar to the liquid than the final crystal structure that will have a local maximum before the final crystal structure is then completely stretching over the bulk. And so this is an example of, this is in accordance with Oswald's step rule, where it was hypothesized that structures that are more similar to the liquid will crystallize first because their free energy barrier is lower. So I want to very briefly discuss the kind of software that I was involved with in driving this kind of science. So I worked on various projects that are done in the group here. First and foremost, the SINIAC framework that I created 4 years ago to help us implement and manage scientific data and scientific workflows that operate on these data. I created the LUX formats package, which is now called Garnet, which helps us translate between various file formats and kind of makes it easier to have different tools interoperate with each other. I've also contributed to our simulation workhorse, Kundi Blue. I've contributed to the GSD file format and the Freud analysis package and the Plato-Vis visualization package. And so I won't have time to talk all about all of this, but I want to just very briefly introduce the idea behind SINIAC. So the idea is that we wanted to have a software framework that really supports us in what we do already, and just make it do it a little better, essentially. So the idea is that we already are operating on file-based workflows. We have a lot of trajectory files and visualization and plots. And one challenge is to manage these data and also connect the data with its origin and provenance. And so the model behind SENIAC is that we have a huge data space represented by this gray blob here, where each of these points represents one data point, and that may be a single number or thousands of gigabytes of data. But the key idea is that we can associate or attach each and every of these points with a specific ID that is then related to the metadata of that data. So that is essentially a database. And the key idea is that the database is directly in the file system. It's very easy to access and manipulate it. And then the second step is to actually implement workflows that operate on these data. So usually you need to generate this data and then make some modifications or collect results. And we want to do this in an automated way, not only for convenience, but also for reproducibility. And so we can define these workflows using the SENIAC flow counterpart here, and then execute these workflows both locally on the computer, on the laptop, or on the leading supercomputers. So this makes it very easy to implement and test workflows, but then also scale them up to leadership class computers. Okay, and so part of this work was not only implementing this software, but actually trying to understand what are the needs of researchers, not only in our group, but also for other groups. And so we did a lot of outreach in terms of presenting this work at conferences. This is Vias Ramaswamy speaking at the SciPy conference in Texas last year. We presented this work at the PyData meeting here in Ann Arbor and various other conferences. And very recently, we're affiliated with the NumFocus organization, which is behind the NumPy package. So with this, I would like to take a moment and thank you all for your support. Specifically, of course, Sharon. I'm really grateful for the kind of environment you created here and for taking me on in your group, and you're definitely a role model for me in terms of how to, inspire people doing science and doing awesome work. I also wanted to thank Sharon for keeping us afloat and for doing all the little and the big things that need to be done. I wanted to take a moment to thank Jens and Josh and Julia and Ryan, who've been great mentors to me and have been really helpful in trying to learn both about software development and crystallography and all kinds of things. Tim, who's been a great friend and mentor. I've actually known him back from Nashville. And I was really excited to learn that he would come here and work with us. And then, of course, Vias and Bradley, you've been awesome friends, and without you, I don't think the whole SENIAC project would have taken off the way it has. And then Jim, who's been amazing friend and co-author, and all the other people that I got to know here. I became friends with. I can't mention everybody. I think you're all great. I also wanted to very briefly acknowledge Ahmed Ismail, who very sadly passed very recently. He was my first advisor in undergrad, essentially, and he encouraged me to go and apply for PhD programs and to go to the US, and I would definitely not be here without him. Peter Cummings, who welcomed me in Nashville at Vanderbilt University, and Christopher Beller, who was one of the first people who worked closely with me on these projects. I want to thank my family abroad and my newfound family and my extended family and friends who've been very supportive and needed to put up with me being gone and all that. And of course, my partner in crime. I really don't know what to say. I love you, and you've been extremely helpful and supportive. You're just an awesome person. Okay, with this, I would like to thank you for your attention. Took a little longer, sorry about that. I'm happy to take questions.
That was a beautiful presentation, beautiful work. The floor is now open for questions. Matthew.
I have two questions that you can indulge me.
Sure.
First, how did you select your hyperparameters for the unsupervised learning type for things like UMath and vector machine? And second, how did you take any extra care in sort of selecting which data you feed to the unsupervised learning, or otherwise figuring out how much of which type of data you feed?
So the question is, how would I tune these clustering algorithms and dimensional height reduction techniques that I showed in the unsupervised machine learning workflow? And the simple answer is that I trained various different parameters and tried to see which ones work best. So there are some things that were crucial. I'm using a Manhattan metric, for example, which is more suitable for high dimensional data, because if you use a Euclidean metric, for example, then all these points become very close together in this high dimensional space. There are some other important parameters, like the min cluster size, essentially. So the HTV scaling algorithm that I didn't introduce, but I use for this clustering, will automatically adjust distances between points, so the cutoff distances it takes into account. But it still needs to it needs to have an idea of what cluster size we expect. The second question was about the selection, with the random selection, and I selected randomly across space and time with no bias in that sense. So, yes.
So, were you controlling like how quickly you're down to something like that? Basically, I'm trying to get a feel for, because you could conceivably spend like 90% of your simulation time with nothing, and then 10% of your simulation time with actual order in the system, and then you might expect your unsupervised learning to learn a lot more about what the fluid looks like than what the solid looks like.
So I made sure to select a window that was mainly including the actual process of interest. But what I didn't show was a complex study, which really only included the process, and I didn't see any difference there.
Yes, and then
So in the first bit at the front, you have this free parameter or free-ish parameter C that's controlling commercial filter. Can you use information about what the gray space RDF is, like the fact that it has nice peaks to determine like what is an optimal choice of C, or what is a good choice of C?
Probably. I mean, we chose these constants empirically, but they do correspond roughly to the length scales in Fourier space. So I assume that you could take the lattice spacing to inform this concept.
So you said you've been kind of shopping this software package around to other groups. From those who have adopted it, what has been the response towards it, and also what do you kind of see the next place for the software package?
So for the most part, I think response was positive, but of course there's a bias. People are going to tell us. But I think the feedback that we got for the most part is that people who are doing work that is very close to the metal, so you're running simulations and you have high computational demand, that is where more complicated workflows are not that suitable anymore, which are kind of overkill and hard to translate between some preliminary study and something that runs on a supercomputer. So the idea really is that we're one step above rolling your own. And if you have these kinds of workflows, then the people are usually very quickly getting the idea and can get use out of this. And in terms of future, I think we found a good problem space, and we have no intention to make this in any way more complicated. Like, we want to make this more robust and better, and maybe solve a few more, or reduce some barriers, but I don't see it expanding.
T and Bradley, Jens, Rosie.
So I think one of the reasons why people like the lineages architecture is it's semi-empirical. Right? Like 6 power comes from T-sum forces, limit dispersion. Yeah, 12 is just, oh, I know I have that on core, so I select 12. Inverse Bose tangent in REM gives you these wacky potentials. So what I like about your method is you smooth it out, right? So can you now backtrack out what kind of forces give rise to these potentials so that we can design some kind of particles and make these crystals or something?
Yeah.
Experimentally?
So I think of course it's challenging. You can't immediately translate from a potential to a real particle or to some shape. So the idea that I proposed in the beginning was to actually create a library of potentials that will assemble the same structure as certain shapes, and so that we can try to map between potentials and shapes. But I think primarily it gives us also a bound on the complexity of the potential. We know how many scales we might need, and we can try to infer that. So we can say, well, we need some attractive, like strong attraction at the beginning, and maybe some repulsion at this specific length scale. And so I think that's something we could use to inform the particle design.
So I have one question from the live stream. Brian asks about filtered IBI, iterative Boltzmann iteration, or yes. Does the optimal filter strength depend on the maximum or minimum target assembly temperature?
I don't know. If the system is cooler, it's going to be more discrete, so we definitely benefit more from the filter. If it's hotter, the density distribution will already be somewhat smoother, so we don't necessarily filter as much. But I'm not sure if there's an optimal filter strength for certain dimensions.
Maybe more comments. So spend only a fraction of the talking about the software development project, but my impression is that Synac has had an enormous impact, not only within the group but also outside, and almost everyone is using it. And those who don't use it know who they are. And so for myself, from my own perspective, it's like I wouldn't have been able to scale up my own projects had I not been able to rely on something like Synac, even however small it is. So I'm wondering if you were to describe the impact the program had on your own work, like how much time you spend on developing, how much time did it save you? Is there anything you can say about that?
Yeah, I mean that's a very critical problem, right? I mean, you build tools to do work, and you need to balance how much time you spend on building those tools. And so it's something I didn't talk about at all, but we've actually published a paper together with us about how you might be able to optimize this kind of process. So the basic idea is that usually you want to really focus on solving certain problems to the point that you've solved them, and don't worry too much about the more general problem. So the case of Synac would mean, okay, I have files that I want to manage. Okay, let's solve that problem. I want to run a workflow locally. Okay, let's do that, and so on and so forth, without starting with like some grand idea of how everything might come together. The key point is that, or the key idea is that you actually, this is like it's like a close to optimal way of balancing these problems, but it also ensures that when you start solving the more general problem, you have a much better understanding of the problem because you already solved the particular one, specific one, and then you start bringing things together.
My impression of those who have adopted SINYAG is that once you're using it, you say, how did I ever survive without it? Yeah? Rosie.
Calm as I'm not a plant. So with the FFREM, it arguably you could come up with two different potentials, like two totally non-related potentials that assemble the same structure. How would you assess the fitness such that you would choose one versus the other?
So the potential and the distribution, density distribution we get is actually a one-to-one mapping, but it is true that we'll have multiple different structures or multiple different potentials that will assemble almost the exact same state. And the fitness function of this comparing target and the desired state will not help us very much there because they're going to be very, very close. And one way you can do this is why we introduced this complexity measures. You can say, well, there are two solutions, but one is a little smoother or simpler than the other. So that would be one way of choosing what the better model.
Cool.
Another from the live stream.
This is me,
and-
actually.
What?
It's actually me.
Oh, sorry.
So yeah, one of the things you talked about with your machine learning analysis of pathways, at the end you had a conclusion about how you can explore two-step nucleations where you might have some kind of order fluctuations or density fluctuations and how those correspond. Can you expand a little bit on what you found specifically in your systems, and also maybe like did you see like if you plotted, say, local density for a particular environment, did you see patterns in that?
Yeah, so I evaluated the density and order of these individual environments, and what I found for all the study systems was that there is some intermediate environment that is between the liquid and the structure. I might not have completely understood the question. So it's about, are you asking about general pathways or?
Specifically with regards to like density and like local density, did you quantify that? Did you study like for those intermediate environments what density fluctuations might have existed?
Let me try to find one about that. So this is a density versus.
Yeah.
This is density versus order for various different particles at different times. So what I'm plotting here is order lineage specialization is as we go from time 0 to time finish, we move both through order and density, so both of these increase, but not at the same rate necessarily at specific times. And we can locate the environment groups that we found using the clustering algorithm in this plot. And we see there's two wells. So the shaded region here means how many occurrences of that particular macro property was counted. And we see there's two liquid states or fluid states here at the beginning. And then these two ones correspond to random hexagonal close packing. And then this is a face of the environment. So we move through this, and we'll have a increase of both. We have an increase of HCP order both at a slightly lower and a slightly higher density. It turns out that actually corresponds to HCP like environments within the nucleus and at the surface of the nucleus, and this is within the rest of the system as well. And the nucleus will have both SEC and HCP environments present, with HCP at the surface mostly, and will then grow and eventually this is our condition.
Thank you.
Did you have a question?
Yes, actually, it's kind of a similar question on the same topic. For
Can you speak a little louder?
Sorry, yeah, kind of a similar question as the one that Bradley just asked. I was wondering if you were able to identify any kind of perhaps a necessary condition for observing or predicting two-step crystallization pathways, perhaps in terms of the local order or density, for instance.
Not that strongly, but what I did see is that local order is always present at every stage of the crystallization. So there's always going to be environment like fluctuations of local order everywhere in the liquid prior to crystallization. So that seems to be a requirement for spontaneous liquidation.
Andrew and Tim.
So the BCC simulation, you mentioned the fluctuation of local order and local density. And for the local order in the fluid, how many particles typically participate that in the BCC? And does that number vary across different crystal structures?
I didn't mention BCC actually.
Okay.
But are you wondering about the relative concentration?
Well, this was the SEC. Yeah, just like the local order in the fluid, like how many particles typically participate in that? Are we talking like 4 particles that come together, or like 16?
Oh, it's more one. They're very well distributed.
So when we're doing this inverse design problem for shapes, we run into a problem where we can design a shape for a target structure. We get the optimal shape for that structure. That doesn't mean that the structure is the optimal structure for that shape. So you can design a shape for a diamond or something, and you run the assembly, and you might get something like FCC. Did you have any similar problems with your FFRM?
So with optimal means not the energy minimum.
It is a fair minimum in the shape space for that given structure. So did you have any cases where you designed a fair potential for a complex structure but end up assuming something similar?
So yeah, I'm trying to relate this because so the equivalent problem would be that so I think I can't quite draw this analogy here because I'm not doing digital alchemy where I'm like finding the energy minimum of the specific potential for a structure on the fly. So I'm trying to design a potential that has a free energy minimum at the target state. I assume that if we were to change the potential on the fly during the simulation, then we would have a similar problem. I don't think I can.
I guess the FFRM wouldn't converge also. You're getting a different structure.
Could you speak a little louder?
Yeah, I guess the FFRM wouldn't converge to the that fair potential if you were getting a different structure. If it was melting into something else. Is that picturing FFM?
So it does happen that there are other structures present, and there's no guarantee for this, but the update step does usually drive into the final structure. And that is because of this relationship between the potential moving force and the parent directions.
Okay, James, you get the last question.
Can I turn it into 2?
It depends how good they are.
Okay. So in your trajectories, you have kind of an overrepresentation of the structures or the data space that correlates to things that are actually in structures, and maybe not those intermediate states or precursor phases. Do you have any method where you're trying to kind of give some importance to environments that may look different from something that's ultimately in typically experienced fluid or in crystal?
So, if I understand correctly, you're wondering if there's a way to emphasize these intermediate environments more? Or
for the purposes of clustering. Because otherwise your trajectories are going to reveal the stuff that your simulations are more climate.
So I don't think that's necessarily true because the manifolds that are generated are of course denser, where we have more points. But that's why we're using the HCD scan algorithm to kind of account for these different densities. But the best solution for this is to use advanced sampling techniques that sample your process less biased and more rigorously or more detailed.
And then I guess a little follow-up to that quickly is if you were to identify some precursor environment, would you be able to use that the identified particles from that environment to generate a GSD, or not GSD, sorry, a GUR focused on those particles in particular for your fast Fourier argument?
So you're asking if the intermediate structures and their density distribution could inform the optimization of potentials?
Yeah, essentially if you could do some kind of multi-state thing where you give some importance to, say, precursor, if you're able to identify it.
So the approach, this iterative approach that we're using, is always based on running a full simulation and trying to get energy minimum for a given potential. The only thing that I could see is to try to optimize directly for these intermediate structures, if they are structures, and then combine the results. But I don't see an immediate way of how we could map between, or we could map together multiple structures into one potential, unless you use something like multi-state IBI approach for epigram. You can optimize for multiple structures at once, but I don't see I don't really see how we could use that to inform the process better for
Okay, let's thank Simon again. You're all welcome to